All right, grade 9s, with your notes out in front of you, we're going to take a look at conductors and resistors here today. So we just got finished doing this FET simulation here, you guys, we built some wire, we got some wire and a battery and maybe a light bulb. Some of you had some of you put a dog and a human hand in between there, which was rather disturbing. But the link to this little exploration lab is on the website if you want to go there. Let's see. Should be right here, this button right here, FET circuit simulation. So if you're at home and kind of forget where we were to get at that, well, there you go. Okay, so let's say we have, I'm not sure if this light bulb's going to do so well right against the battery. What do you think? I don't know, maybe it'll work. Let's do something a little more realistic here. Let's connect. Now, what happens if I hit this switch? Oh, nicely done. Look at that. We've got a 9-volt battery here. And we've got the electrons are flowing from the negative out through everything to the positive. Over here, look at this button over here. I don't know if you guys check this one out here when you're working with this. But remember, electron flow and conventional current flow is actually opposite direction. So this is the positive end of the battery, and the conventional energy that the light bulbs would use would technically be viewed as coming from the positive, all right? The positive. So it's a bit of different. We're talking about electrons, they flow the other way. The positive sort of carrying charge here replaces them as they flow. Anyways, it's a little confusing, but you can play around with this. You can put different things, like you can put a coin. Okay, we can take a coin here. We can cut this. Let's put a coin in between there. I'm not sure. What do you guys think? Is this going to actually work or not? You think it will? Okay. So if I close the switch, oh, look at that. It actually does work. So it seems that this is a conductor of electricity. A coin might be a conductor of electricity. What about a paper bill? Okay, dollar bill here. Did you guys try this? Yeah, you don't think it's going to work? I'm not sure why it won't work. Money is energizing. Oh, boy, I like having money. I don't know. What about you guys? Oh, wait a minute. What's going on? Oh, nothing's happening. Huh. I guess that paper doesn't conduct electricity very well. Hey. So these are the kind of things that you'll be able to explore in this here lab. And today we are going to talk about conductors and resistors. So you got your notes out in front of you. Some materials allow current to pass through them easily, while others do not. We just saw in that simulation the coin allowed electricity to flow through it. The paper money did not. So a conductor, this is not the guy on the train that goes toot toot, not the train conductor, but a conductor is a material that allows electric current to pass through it easily. That's what you call a conductor. So if a material is a good conductor of electricity, it allows electricity to flow through. Metals are conductors of electricity. Metals are good conductors. However, some are better than others. So we would use metal wiring inside the walls to connect our switches to our lights and our power source. And electricity flows through, copper wiring and that sort of thing really well. There's obviously insulation on the outside of those wires so that if you accidentally touch them, you don't get zapped. But electrical wiring has metal on the inside where electricity can flow rather smoothly. Now, there's a little, I put a little comic here for you. This little fish here says, I'm usually not allowed to play with electricity, but I'm sure Mom won't mind me playing with you. I don't know if you get the humor in that. This is like a little baby electric eel, maybe. So he's not playing with electric, although electric eel has, the ability to, zap, a little electricity flowing there. So not to play with electricity, but can probably play with your little buddy eel.
Do you know why the electric fish
Well, why? It'd be the chemical reactions that are happening, and that sort of thing inside the eels there. Yeah, question?
So if you were to
So the question was, if an electrical wire, okay, that has, let's say electrical wire has, let's do red, copper, and on the outside it has this insulation that's wrapped around, right? So if it's touching something out here, okay, the insulation works so that the electricity that's flowing through the metal does not get through that insulation. That's the whole point. It's covered with this insulation. It's like a rubbery, plasticky material, right?
Did it have that insulator? Would it?
Sure. If it was a bare wire and no insulation like that, sure. And if the electricity is passing through here and it touches some metal object, then the electricity could go through here and not get to its intended target, right? For sure. Yeah, absolutely. So that's why we have insulation. That's why there's not bare wires running through the walls. Yeah, for sure. Okay, water is a very good conductor. That's why water and electricity don't mix. So if you're in the bathtub or something and you want to listen to the radio or something, or your CD player or whatever it is, and you bring your CD player and put it on the edge of the tub while you're having a bath or whatever. I don't know who has baths anymore. I think old people do. Actually, I do. Wait a minute. What? So anyway, so you don't want to like have your CD player or whatever fall into the tub or something. It would not be good. And you don't want to be swimming in a lake when there's lightning, right? We talked about this before, because water conducts electricity. So if lightning strikes water over here in this part of the lake, conceivably it could travel very, very far and zap whoever's going to be in there. So that's not good. All right, resistors. Oh, yeah, question? Resistors, a material that slows the passage of electrical charges. Where are my notes? A material that slows the passage of electrical charges. Resistors. There we go. So just to highlight what you guys have for blanks. A material that slows the passage of electrical charges is called a resistor. Resistors are able to slow the amount of current that flows. This is going to be very helpful for electronic equipment and different things, and you'll see different resistors like on motherboards of computers and different things like that, because there's an amount of current that needs to flow to certain parts but not to others. It'll be too much for some of these little parts, but not enough for the larger parts that need more energy. And so you have resistors that are placed in the path of different things to protect them or to regulate the amount of current. No, later. The greater the resistance of the material, the greater the amount of energy the electrons give up as they pass through it. I'll read that again. The greater the resistance of the material, the greater amount of energy the electrons give up as they pass through it. So if you have high resistance, the electrons are going to give off more energy to that thing. Okay, it's gonna literally take more energy to plow through this resistor. Now, some of the resistors are so resistant that energy just doesn't bother. It'll take another path if it's easier, and that's why the sheathing or the insulation on electrical wire is so helpful, because we have this metal, this steel, the copper wiring. So electricity says, hey, I've got a real easy path through the wire. I don't want to try and blow through this coating, this resistance. So it just goes along the only path that it is reasonable for it. Electrons give up energy as heat and light. Heat and light. So we know from our study of the light bulbs that one of the ways that the energy can be released is light, obviously. But if you touch a light bulb, especially a conventional, kind of an older style light bulb like this, if it's been on for any length of time and you touch it, it is extremely hot. So light and energy are the form of this energy release. So this characteristic is what makes them useful in many household electrical devices. So as I said, the heaters, right? If you turn on an electric heater, it's going to give off a lot of heat. Not a lot of light, but a lot of heat. Light bulbs will give off a lot of light and a little bit of heat. So this is very useful. Resistance. A situation in which some electrons are allowed to pass while others are not. So if we provide resistance or put a resistor in our electrical equipment, some electrons will be able to pass through and give their energy, but others won't. So we're limiting that. Quietly. Okay, a variable resistor. Great nights. A variable resistor. Next page for your notes there. A variable resistor is a device that can be used to control or vary, that's why it's variable, to vary the amount of current in an electrical circuit. This is done by increasing or decreasing the distance the electrons must travel from source to load. So this is a picture of some controls on an oven, and you can have the oven at 200, and this would be corresponding to the temperature inside, 200 degrees Fahrenheit, or 350 is a typical cooking temperature. 500, boy, if you get right up here, there's also broil, which is like super duper hot. Where the elements are, and if you look inside your stove when the stove is on, if you look inside that glass window there, you'll see that it's glowing red, right? The elements on the bottom are glowing red. Broiling, you have the elements on top that's really close to the food, really hot temperature, really glowing red. And so this dial right here controls the current going into those elements. And the elements are basically, they're kind of like resistors. And so if you're pushing electrons really hard through these elements, they glow red and they get really hot. Okay? Question? All right. What about insulators? Okay, there's resistors and then there's insulators. A material that does not allow electrons to pass through easily from one material to the next is called an insulator. Oh, that's weird. When you think about insulation, wow, what happened there? Insulator. When you think about insulation, you think about something that keeps things warm, right? That's what I think about. If you have insulation in the walls of your house or in your roof, in your attic, insulation on your garage, or insulation, if you have a big heavy coat on in the winter, that's insulation for you, right? So it resists the flow of heat, okay? Or in electricity, we're talking about it doesn't allow electrons to pass through, to give off its heat or light energy. That's called an insulator. Insulators are used to protect us from electrical shocks. Now the picture I have here below, this is a pair of wire clippers here, and notice the handle is like covered with a kind of a rubber insulating material, so that if you do cut a wire that has some kind of electrical equipment, you have some protection between you and the metal instrument here. So insulators are used to protect us from electrical shocks. They create a barrier that keeps the electrons traveling along a path from source to load. So they create a barrier that helps keep electrons traveling along a path from the source to the load. Now the source would be like a battery, load would be like, your light bulb or whatever it's powering. Without this barrier, many of electrons would fly off the conducting wires and be lost to the environment. So we want those electrons to go exactly where we want them to go, not just to kind of dissipate and go off into everywhere. As a result, the electric current would be greatly reduced. Okay, so as insulation or something like that, we don't want electricity flowing through those things. Materials that make good insulators are plastic, glass, fiberglass, and rubber. Those are the blanks you're going to fill out in your notes there. So you have this diagram. I think it's on just before the last set of notes. It's on the previous page for you guys. But so this diagram here, this is like a telephone pole with electrical wires. They might be telephone wires. They might be electricity wires. But what you want to notice are these little glass things that the wires are contacting. So you wouldn't want the wires to contact these metal braces, because the electricity would not stay on the wire. It would pass into the metal braces. You don't want it resting on the wood or anything like that. You want it the path of electrons to flow through these wires as seamlessly and as easily as possible. So whenever they have to put these wires onto these telephone poles to keep them up off the ground, they would have some really strong insulators. So the electrons traveling here don't say, oh, hey, let's jump off here, boys, and let's go down the pole and try and get to the ground. No. They're going to keep going on their easy path because this is a great resistor. So you'll see these little glass things, and they have different things that they use to different materials and such. But that's why you see these little things on telephone poles and transmission poles and stuff. Mm. So the disturbing story that I have to tell you here is when I was a kid, I grew up on the farm, and one time we came home after a weekend, and so we had a kind of a telephone pole, a electrical pole like that. It had the electrical wires that were feeding our house and stuff like that. And we came home, and we were quite shocked to see at the top of the the pole, right about here, was this big. It looked like it could have been like a raccoon, or it could have been like a badger or something like that. I'm going to say it's probably a raccoon. It was difficult to tell because it was literally fried, and it was hanging. So it was like draped over. It was draped over the telephone pole. Its legs were like hanging like this, and its paws were hanging, and literally its head its mouth, okay, was like in the process of chewing this wire or something. Like it was like it died just like this thing. And it was like sitting on the pole, and its paws were like over the wire, and its mouth was on the wire. It totally got up there and got mixed up in the wrong spot, and it sat there. And the thing was like all dried up and like black, and the fur was like sticking out, and like it was like it's up at the top of an electrical pole. Like we can't get up there and take it off. We'll get electrocuted ourselves. So we just left it there. It just like disintegrated. There's this like skeletal remains on there forever. It's like hilarious. It wasn't hilarious. I mean, this thing died, so that's bad. Sorry. Moment of silence.
But it's a raccoon, so.
But it's a raccoon. Or whatever it was. Don't know what it was. It could have been a small child. I'm not really sure. That was dressed up in a Halloween outfit. I don't really know. I don't know. Maybe, yeah, I don't know. Hopefully it wasn't a small child that was dressed up in a Halloween outfit, but. Okay, let's see what else we got going on here. Class is almost over. Okay, so conductors, resistors, insulators, with your little FET demonstration there. These are just a list of some things that, you don't have this list on here, but what I want you to do is I want you to list, and you don't have to list these, I want you to list, at least 5 things, at least 5. So let's see, what's that? Greater than or equal to 5. 5 things around your house or around school or out in the yard. Different kinds of materials that may be, you think, conductors or resistors or insulators. So conductors, electrons pass easily. Resistors, electrons are like, Insulators, electrons, no. So I want you to go ahead and make a guess there, and let's bring our ideas back, and we'll talk about what we came up with. All right, that's your lesson on conductors, resistors, and do that tonight. That's your only homework. Come up with those 5 things and give a guess.